Hello, the purpose of this video is to prove the sequential compactness theorem. Before I get started and talk about what sequential compactness theorem is and proving the first theorem, theorem 3.3, let me talk about what is the importance of the sequential compactness theorem and what's the bottom line in the sequential compactness theorem. Oftentimes when dealing with sequences, we would like to extract some convergent subsequences of that sequence, especially when we are dealing with continuous functions, which is something we will talk about later. Of course, there are plenty of sequences that aren't convergent. For example, a sequence like the alternating sequence 1, -1. So this sequence of -1, 1, -1, 1 is a divergent sequence. However, we can extract a subsequence of that is convergent. For example, the subsequence of all -1s. So the objective for today is to basically study that. So given a sequence, can we create a convergent subsequence of that sequence? And the way we deal with that is that we first extract a monotone subsequence and then we use monotone convergence theorem, which is why we will prove this theorem first. So the first theorem is every sequence of real numbers has a monotone subsequence. So let's see, again, as usual, we're going to talk about the scratch work on the right, and then we'll write down the actual proof on the left. So you have a sequence A1, A2, A3, etc. I would like to create a subsequence of this that is monotone. So let's just start from term A1. If there is something more than A1 in the sequence, let's say A4, then I will choose that. So I'm going to look for a subsequence that is increasing. Let's say there's something more than A4, perhaps A10, that is more than that. And if there is something more than A10 that is more than A10, if there is a later index that A sub that index is more than A10, I will pick that, and so on. If I can continue this process forever, then I will be done. So when is it gonna be impossible to continue this process? Let's say you are stuck at A11. Let's say you're here and then there's nothing more than A11. So when does that happen? That happens if A11 is more than A sub n for all n more than 11. And if that happens, then this would be an index that I would have to avoid. So if there aren't any indices like that after a point, then I can repeat this process. Okay. And what does that mean? It means these indices 11, like 11, that A11 is more than everything after that. If there's only finitely many of them, then I can do the exact same process that I explained. And if there are infinitely many of them, so A11 is more than everything after that, then there is some other index after that. So let's say A17. And A17 we know is more than everything after that. So A17 is more than, let's say, A18, which is also one of those indices. Then you can create a subsequence that is decreasing. So the bottom line, we need to talk about these indices like 11, the terms like A11, that are more than everything after them. So we will start with naming these terms as peak terms. So that these are the terms that they peak and they are larger than, so A11 is here. And it's larger than, so if you look at that kind of the graph, A11 is here, and everything after that is less than A11. All of the terms after that are less than A11. So let's call these peak terms. So okay, let me first start with naming the sequence. So let an be a sequence. So that's the first step. A term or an index, sometimes they call it peak indices. An index n is called a peak index if and only if an, so that term is more than am for all m greater than n. So as we discussed, if there is only finitely many of these terms, then I can create a sequence that is increasing. So suppose there are only finitely many peak indices. Let n be such that so we take a positive integer such that if n is greater than or equal to n, then n is not a peak index. Okay, so we start from term an. So since a capital N, since a capital N is not a peak index, there is some term after that. There is n1 in n, n1 greater than n, such that a capital N isn't more than a capital N, a sub n1. A capital N is less than or equal to a sub n1. It is because it's not a peak index. It is not more than everything after that. Now, again, since n1 is not a peak index, because we know there are only finitely many peak indices, everything after capital N is not a peak index. So since n1 is not a peak index, there is some n2 in n with n2 greater than n1 such that a n1, since n1 is not a peak index, a n1 is not more than, so it means it's less than or equal to a n2. Similarly, for a given nk, since it is not a peak index, there is some ak plus 1 in n with nk plus 1 greater than nk such that a nk is less than or equal to a sub nk plus 1. Therefore, an, an1, an2, etc. is an increasing subsequence. So this was the case where there are only finitely many peak indices. Okay, so now, so this was the assumption that we made. Suppose there are only finitely many peak indices. Now assume that there are infinitely many peak indices. Now suppose there are infinitely many peak indices. Now, so assume that this time we're going to call them M1, M2, M3, and so on, are peak indices. Now, M1 is a peak index. Since M1 is a peak index, A sub M1 must be more than A sub M2. Why? Because a peak index gives you a term whose value is more than everything after that. So that means AM1 is more than AM2. And then similarly, since MK is a peak index, AMK is greater than AMK plus 1. And that means A sub MK is a decreasing subsequence, which is what we wanted. So this finishes up the proof. Okay, so here we showed that in each sequence that you take, there's a subsequence that is increasing or decreasing. There's a monotone subsequence. This is a very interesting theorem because it's actually not a theorem from real analysis. It doesn't really have anything to do with convergence or Archimedean property or completeness axiom. It doesn't have anything to do with those. This is more like an exercise, I would say maybe a pre-calculus exercise. But the application is very important in advanced calculus or real analysis. Okay, so let's prove the next theorem, which is the main application of that theorem above. In this class, the theorem that we just talked about is only going to be used in the context of finding convergent sequences. So really, the theorem 3.1 is the main theorem. Every bounded sequence has a convergent subsequence. Why is that so? Because if you have a bounded sequence, then you can find a monotone subsequence by theorem 3.3, and then by monotone convergence theorem, that subsequence must be convergent. So let AN be a bounded sequence by theorem 3.3. AN has a monotone subsequence. Now, let's call it perhaps ANK. Since ANK is bounded and monotone, it converges. And that's exactly what we wanted to show. We wanted to show every sequence that you take, it has a convergent subsequence. Now, this brings us to the definition of a compact or sequentially compact set. Okay, so any set that satisfies this property that every sequence in the set has a convergent subsequence is called a sequentially compact set. A subset S of R, so just to state that more rigorously, A subset S of R is said to be compact, or sometimes they call it sequentially compact, if every sequence in S has a convergent subsequence that converges to an element of S. So every sequence has a subsequence that converges to an element of S. So not just converges, but it also converges to an element of S. Okay, so before we talk about an example of something that is compact, let's look at a couple of examples that are not compact. The following are two examples of sets that are not compact. So the set closed interval from 1 to infinity is not a compact set. So we have to negate this statement. Every sequence, so we need to find a sequence that has no convergence subsequence, or if it does have a convergence subsequence, the subsequence converges to an element outside of S. So in order to show a set S is not compact, we need to find, so for every sequence we have to show there is a sequence. We need to find a sequence an in S that has no convergent subsequence that converges to an element of S. In other words, if A and K converges to some element, then that element is not in S. So this is what we need to prove. So let's look at part A and see what is the sequence that no subsequence of that converges to an element inside 1 comma infinity, inside the interval. So if you think about that, you can create a sequence that blows up. So consider this sequence. Consider an equals n. We know that this sequence n approaches infinity by the Archimedean property, and thus every subsequence nk also diverges to infinity, and therefore an equals n has no subsequence that converges. Thus this interval is not compact. In fact, the sequence that we have doesn't even have any convergent subsequence. Okay, so we're going to look at the next one. We have the interval from 0 to 1, and we want to find a sequence inside that interval that doesn't have a subsequence that converges to a number between 0 and 1. So we're going to create the sequence in a way that it converges to something on the boundary. If you look at the interval from 0 to 1, you can create a sequence that converges to either 0 or 1. So let an be 1 over n. Although since 1 over 1 isn't in the set, I'm going to make that perhaps 1 over n plus 1. Now, by an example, an converges to 0. So thus, every subsequence of an also converges, but it converges to 0. And since 0 isn't in this interval, the interval 0, 1 is not compact. We found a sequence that has no subsequence that converges to an element of the set. These are the two obstacles that we face. The first one is our interval is unbounded, and the second obstacle is the interval is open on one side, at least on one side. So I can summarize that in the kind of like the conclusion of that would be, perhaps if we can avoid both of those two issues, we would get something that is compact. And in fact, that is the case. The sequential compactness theorem. Every interval of the form closed interval from A to B, where A and B are real numbers, is compact. So if you take a closed interval, it would always be compact. So what do we need to show? We need to show every sequence inside the closed interval has a subsequence that converges to an element of AB. Okay, so let's start with AN. A sequence in AB. Now, since this sequence is bounded by theorem 3.8, the one that we 3.4, the one that we just proved, every bounded sequence has a convergent subsequence. It has a convergent subsequence. So by theorem 3.4, AN has a convergent subsequence A sub nk. Now, this subsequence is convergent, and it's also between A and B. So assume A and K approaches some L. Since AB is closed, L must be in AB. And that is why AN is compact. So let's just write down one more sentence here. Therefore, AN has a convergent subsequence whose limit is in AB. And that completes the proof. Okay, so let's just recap again. So what we did was we showed that every sequence of real numbers has a monotone subsequence, and then if the original sequence is bounded, the monotone subsequence is also going to be bounded, which means it would be convergent. Therefore, every bounded sequence has a convergent subsequence, and that is what gives us the monotone convergence theorem. Okay, so if you would like to continue with this course, real analysis or advanced calculus, feel free to subscribe, and I will see you in the next video.